I guess this works better. I hope we get a hands up or sign from the audience online. Thanks. Okay, cool. All right, welcome back. I will start my talk with a bit of introduction on opinion dynamics and homophily in spatial systems. And then I will talk a little bit about the emergence of echo chambers, in particular configuration or regime of the system. Then I will propose our solution, which is called Messenger, to break these echo chamber. The talk will be a little bit heavy on model, so please hold to your seat really tight. Yeah, so I guess you already have heard about opinion dynamics, especially in the first day of the conference. But here I would like to also resonate from this point by Mirta Galicic and Olson on the fact that opinion dynamics can be at the core of so many social challenges that we face today, including spread of misinformation, polarization, and echo chamber. And probably this is one of the famous challenges where the information that we receive is seemingly diverse, but probably it is filtered out by social media or even by our tendencies to receive only the reaffirming information to ourselves. And there are so many opinions out there that are kind of filtered out. So that would be the focus of my talk today. One of the models that is usually used is dates back to a few years ago, maybe decades. It's naive social learning of the GROUT, which is basically the average or weighted average of whatever the opinion of each agent is and whatever the neighbors are sharing. So in short, it's basically nothing but the diffusion of information on the network. So I guess there are other terminologies that call this conformity as well. So what happens is basically under a specific condition, if the network is connected enough or strongly connected in directed networks, there's a consensus happening. And that's interesting. But usually, most of these models fall short of explaining how or why these opinions come from or where they come from. So we think of spatial embedding as nicely as Seth put on the first day, that life is collective, life is spatial, and in this work we cannot agree enough with that. So we define this information landscape for agents. So compared to the previous model that there's no space where these nodes belong to, we put our nodes or agents in this particular space, and that's where the information comes from. So it can be any arbitrary landscape or function like multimodal, linear, nonlinear, and so on. One more thing that you need to do when it comes to space is to think or reconsider network as a spatial. So compared to random network or any other type of network, we need to define space if two nodes, like the links, are available if two nodes are adjacent enough, are close enough to each other. So that's the second modification. The next part is about homophily. So you need to also, because we had this notion of homophily in our model, we needed to redefine homophily in space. Just to talk a little bit about homophily, it's in short, it's disproportional tendency to interact with like-minded agents. So in random complex networks, this is how it's classically modeled, that there's a probability to interact or rewire with other nodes, and that rewiring has or is proportional to some attributes of the nodes. So if you have less open-mindedness and like over time, you see that these clusters emerge where they have very homogeneous within collective or within cluster opinions, but there's no information transporting across these clusters. So this is echo chambers and homophily in short. But in space, you don't have the luxury of potentially interacting with any node, regardless of their position in space. So what we did was to define an objective function, which is a dissonance. Dissonance is basically the difference between what you measure from your information source and what your local peer believe in or are reporting. And each agent tries to minimize that differences. It's kind of an active movement or active drive for agent to move in a space and either find information that matches their social local agreement or find neighbors that match or agree with what they receive as an information. So if you put and combine these two components of homophily and conformity in space, this is basically what you get. It's a very scary optimization algorithm or optimization problem with lots of local minima. It's stochastic and it's dynamic. And if agents follow a very simple pseudo gradient, not even gradient descent, they kind of end up being on this contours, on this spatial formation of themselves. And they kind of agree on, like they achieve a consensus, not only in the opinion domain, but also in the spatial domain. So what you get for free as a side product is this behavior which we called contour capturing. And it kind of answered two questions. What is the mean value of the information and where it is located? And we tested this on different environments and it works. It's kind of adaptive to or robust to this different distribution. But apart from the cool figures and animations, you can also implement this on synthetic system, and we use this famous or infamous kilowatt system that we had. But I'm not going to talk about it today. If you're interested or curious about robotic implementation, please check these two our papers. So, but the interesting part probably starts where things become more complex even. So from our implementation on real world of these very limited robots, we found that in a specific regime where communication is limited, then we see that the number of clusters by the end increase. So we have this, I don't know, kind of critical, if it is not a too strong word, that below that, we see that the collective kind of falls apart. This is what it looks like. I probably need to fast forward it. So by the end of the simulation, we have these clusters that are, again, homogeneous within themselves. There's no link across them. There's no information being transferred from one cluster to another. And this is kind of how the objective function looks like. There are so many empty spots where agents do not know what to do. All right, so that was a problem. Then we thought of, okay, how can we bring back the connectivity, or how can we break these echo chambers? And a potential solution is probably to let loose of the constraint or the pull of homophily. And for that, we define a new role for each agent. Whatever that I already thought of is, talked about is the exploiter role, the normal role, which is kind of an exploiter and exploits the information because it uses the local and social information. It is also greedy in a sense that it tries to minimize the homophily in a greedy manner, which is opposed. In comparison, we have this messenger role, which can move freely in space, free of homophily, but it doesn't update its opinion. So it's kind of a data that moves around in space. So we are using the mobility of agents to carry data. All right, so this is what I already showed to you. But with messengers, we see that we are able to bring the consensus back over time. You can think of messengers probably as stubborn agents or zealots. That's also possible. I can also, I usually think of them as campaigns of information where they don't update, they just shout their opinion and they don't care about what comes back to them. So over time, you see that the consensus is back. We can also look at the opinion development over time. So that potentially can work, but the question is who should be the messenger and for how long they should be messenger. So that's so we need a decentralized mechanism for agents to provide a switching mechanism, and we use this Markov process. It suggests two-state switching based on these two transition rates. So each agent at each time decides whether to be in the exploiter state or in the messenger state. If we look at single agent state over time, this is how it looks like. By changing these two rates, you can change the time scale that each agent stays in either of the two states. On the collective part, on the collective level, two properties are being changed when we change these two parameters. One is the population of messengers. So you see that on this corner, we have all exploiters. On this corner, we have all messengers. That's the messenger ratio. The other property that we change is the time scale of switching. So if I combine these two in an animation, probably that's how it looks like. So on the top right corner, we have very fast switching. So each agent switches its own role probably every other time step and experience the true role. It is kind of the generalized sort of agent. On the other hand, we have these spatialized agents that never switch, and whatever role they have in the beginning, they stick to it for the lifetime. So when we applied this in our setup, we found some interesting optimal regions, which I'm going to talk about, and then my talk will be over. So on the far right bottom extreme, we had this all exploiter where greedy behaviors is observed, the echo chambers emerge, and that's the boring probably setup or configuration. On the other extreme, we have all messengers. So if we recall messengers being data that moves around, so we have this data, but nobody's there to take the data and integrate it. So you see that opinion doesn't get updated. So that is one side of the trade-off, but the optimal zones are or lie in the middle ground, which I'm going to show you in a minute. So here we have, again, if you remember the switching rate, we have very fast switchings here. And this behavior could be seen as an enhanced exploration. So you see that agents only switch for a short time and they come back, and during that short time, they're able to get out of the local minima. There's another optimal zone here where agents are mostly messenger, or like all messengers, but they switch for a very short time back to exploiter and integrate the information. This is maybe the data conservative sort of configuration, but you see over time the opinions, if I can find my cursor, yeah, opinions converge to a consensus. And on the other corner of this regime or this parameter space, we have specialized messenger, and we only need a few of them, like 3 out of 100, that can carry their opinion around and find agents and kind of convince them to go to somewhere else. Yes, so that is that. I need to probably split that up. You also see that these 2 and 1 probably in the middle are the messengers. They never updated their opinion and they stick to that, although they walked around in the space. Okay, with that, I'm going to close, but I want to highlight a few things that spatial embedding makes a difference. Limited connectivity and exploration lead to echo chambers. Stubborn agents, although maybe not very intuitive, can enhance the effective connectivity and bring consensus back to the collective. DMP, or dichotomous Markov process, is a cool tool for switching mechanism. There are trade-offs that you need to consider. Information versus integration is one, generalization versus specialization is another one. With that, I would like to thank you for your attention.